In this video, we're going to talk about a fundamental principle of counting. We're going to write n of s to represent the number of elements in the set S. So let's do a quick example just to see what that would look like. Let's say we have the set A that has 3 elements in it, A, B, and C. So we would write n of A is equal to 3. Let's say B is the empty set. So we know from our previous video, the empty set is the set with no elements in it. Then we would write n of B is equal to 0. So this video is called the fundamental principle of counting, which means there's an important counting rule coming up. And here it is. I'm going to put a star beside it. So the name of the rule is called the inclusion-exclusion principle. And the rule says the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. So let's try an example and just confirm that this rule seems to work. So I've rewritten the inclusion-exclusion principle at the top of the screen, and what we're going to do is just confirm that it works for the given sets. So let's say A is WXY and let's say B is XYZ. Well, in order to confirm the inclusion-exclusion principle, we'll want to know what A union B looks like and what A intersect B looks like. So let's calculate those first and then we'll confirm our rule. So A union B represents the elements that appear in A or B or both. So that would be W, X, Y, and Z. A intersect B represents the elements that appear in both sets. So that would be X and Y. Okay, and from there we have enough information to confirm our rule. So let's look up to our inclusion-exclusion principle, which we've got up at the top of the screen here, and let's look at the left side. So the left side is saying number of elements in A union B. Well, we've calculated A union B and we found out that there are 4 elements in there. Okay, so that's the left side of the equation. For the right side of the equation, we want to calculate number of elements in A plus number of elements in B minus the number of elements in the intersection. And the point here is to confirm that that comes out equal. So what we're looking for is for this number to equal 4. So let's just confirm that. So number of elements in A is 3. We're going to add that to the number of elements in B, which is also 3. And we're going to subtract off the number of elements in the intersection, which is 2. So 3 plus 3 minus 2, sure enough, that comes out to 4. So now let's talk about a better way to visualize this so that we can understand on a deeper level why the inclusion-exclusion principle is true. So we're going to use a tool called a Venn diagram to visualize some sets. So let's look at a few examples here. Let's imagine a situation where we have 2 sets that we care about, A and B. So we're going to represent each of the sets as a circle. So this first circle represents the set A, second circle represents the set B, and this rectangle around the outside represents the universal set, or it represents all the elements that we care about in a particular problem. So we've just labeled our 2 sets here, A and B, and we're going to look at a few different situations where we just shade in the regions corresponding to the relevant set. So if we want to represent the set A, then we're going to shade in everything inside the circle of A. So that would be everything in here and everything in here. That's a visualization of the set A. If we wanted to represent the set B, shade in everything inside the circle of B. To represent A intersect B, remember the intersection represents the elements that are common to the 2 sets, so the elements that belong to both sets. That would represent just this region here. If we wanted A union B represents all the elements that are in A or B or both. So we would have all the stuff in here, all the stuff in here, as well as all the elements that are in both sets. And if we wanted something like the complement of A, remember that's just another way of saying not A, then you would shade everything that's outside the circle of A. So you'd shade this region here and you would also shade this outer region. And that's actually why we need the rectangle, is just to represent that we're taking all the elements that are not in A, but that are in the universal set. So that's a way to visualize sets, and these diagrams here are called Venn diagrams. So let's use Venn diagrams to understand why the inclusion-exclusion principle should be true. So let's think back to our previous example where we had the set A equal to WXY and we had the set B equal to XYZ. There are a couple of ways of drawing Venn diagrams. So first way is we can draw the elements into the diagram. So our diagram is always going to start with a rectangle. We are going to draw a circle to represent each of our sets, and we're going to allow those circles to overlap because in general, two sets will have some elements in common. So let's try to place the elements W, X, Y, Z in the appropriate positions. Well, X and Y are in both A and B. W is in A but not in B, so it should be drawn over to the left. And Z is in B but not in A. And so that's a Venn diagram representing the elements. Now, when our sets get bigger, it's not so convenient to write the individual elements into the diagram. So what we'll sometimes do is just talk about the number of elements. So we've got our universal set. We've got our sets A and B represented by circles. We're going to allow those sets to overlap. And we're not going to write down W, X, Y, Z. We're just going to write down the number of elements in each region. So there are two elements that are in both A and B. There's one element that is in A, but not in B, and one element that is in B, but not in A. And when we draw this sort of Venn diagram, this is where we can really understand what the inclusion-exclusion principle is saying. So I'm going to write out the inclusion-exclusion principle one more time. It says number of elements in A union B is equal to number of elements in A plus number of elements in B minus the number of elements in A intersect B. And looking at this diagram here, let's understand why that should be true. So the left side says count everything that is in the circle of A or the circle of B or both. So we'd be adding up these numbers. We'd say 1 plus 2 plus 1 is 4. So that's the left side. Okay, now let's think about the right side. If we add up the number of things in A, we're looking at all this stuff here. So that would be 3. If we look up the number of elements in B, you'd be shading those two regions and you'd say, okay, 3 elements in B. But the problem is we've overcounted. See, this 2 has been counted twice because it belongs to both A and B. So that's why we need to subtract off the number that we've overcounted. And that number that we're subtracting off is the number of things in the intersection. So if you subtract it off, then you've no longer counted it twice, you've just counted it once. So that's why the inclusion-exclusion principle works. So here we have more of a real-world problem where we're going to apply the inclusion-exclusion principle. A company has 300 employees, 275 are full-time, and 230 are permanent, while 285 are full-time or permanent. How many are full-time and permanent? First thing I might suggest here is that we just come up with a shorthand notation. So let's write F, capital F for full-time, and let's write capital P for permanent. So we could apply the inclusion-exclusion principle. The way we had it written before was number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersect B. But in this case, we're not talking about sets A and B, we're talking about F and P. So we're just going to modify the names of the sets. That's something we'll do quite a lot. So number of elements in F union P is equal to the number of elements in F plus number of elements in P minus number of elements in F intersect P. So let's plug in the information from the question. We know that 275 are full-time. So that's N of F. We know that 230 are permanent. So that's our N of P. And we know that 285 are full-time or permanent. So that means full-time or permanent or both. Okay, that's giving us our number on the left. That's our n of F union P. So to complete this equation, we're still subtracting off this unknown number in F intersect P. All right, so let's do a little bit of algebra. So let's move all the numbers over to the left side. We got 285 minus 275 minus 230 equals the negative of the number that we're looking for. And if you grab your calculator, this works out to negative 220. And so that makes sense. We've got negative signs on both sides. And remember that you can multiply or divide an equation by anything you like. So we're just going to divide both sides here by -1, and we'll have 220 is equal to the number of elements in F intersect P. So let's look back at the actual wording of the question. The question was, how many are full-time and permanent? Well, that is exactly what we've got here. Number that are full-time and permanent is 220. So I'll just write that in a box so that we're clear that we've found our answer. So your universal set here would represent all the employees at this company. And we've got two sets that we care about. The sets are just representing properties that we care about. So we care who's full-time, who's permanent. And what we've just figured out is that there are 220 people who are full-time and permanent. So let's see if we can figure out the other numbers in this diagram. Let's go back to the question. Well, one thing we know is that there are 275 full-time employees. Those 275 employees are sitting inside this circle for full-time. So if we ask how many employees would be in this region here, what we'd have to do is go 275 minus the 220 that we've already accounted for. So that would give us 55 people here. So in total, you've got 275 full-time employees. 220 of them are also permanent, and 55 of them are full-time but not permanent. So that's what we're seeing so far in our diagram. So in a similar way, we could figure out this number. We know from the question that 230 employees are permanent. So if we wanted to figure out this number over here, we would say, well, there are 230 employees total in the circle for P, but we've already counted for 220 of them by filling in this middle region. So that leaves 10 employees out here. So 230 permanent employees in total. 220 of those are also full-time. 10 of them are permanent but not full-time. And then as a final step, if we wanted to fill in this outer region here, let's think about what that outer region represents. So it's outside the circle for F and P. That means we're talking about employees who are not full-time and who are not permanent. Well, the key piece of information here is that we were told that our company has 300 employees. So we're saying this entire rectangle, all the people that we care about in this problem, this entire rectangle contains 300 people in total. So if we want this outside number, we're going to go 300, and we're going to subtract off all the people that we've accounted for already. So 55 gets subtracted off. We subtract 220, and we go minus 10. And we can grab a calculator and just figure out what that number is equal to. So that leaves us with 15 people. So those 15 people are sitting out here who are not full-time and not permanent. So the Venn diagram was not strictly necessary to answer the question, but I think it does give an intuitive feel for what we're doing. So we will be using Venn diagrams quite a lot in our next section, and therefore we're just going to do a little bit of practice here with drawing some Venn diagrams. So let's draw A intersect B complement in a Venn diagram. So what I would do is draw our classic setup for a Venn diagram with two sets. So we've got set A and set B represented by circles. We want to allow those circles to overlap. And let's first shade in what the set A looks like. So we're just shading in everything in the circle for A. And we're going to draw a series of these diagrams. So next set that we might want to understand is the complement of B. And then once we've got A and the complement of B, then we could think about performing the intersection operation. So that's the logical flow of how we're going to draw these diagrams. And so by the third diagram, we'll have our answer. So for each diagram, you're just drawing this classic setup. You've got your two sets. Good to label them A and B. And let's shade in the complement of B. So we're shading in everything that is not in B. You get two regions shaded. You get this sort of left side of the circle, and you get that whole outer region. All right, so now third diagram, same setup. You've got your two sets. You're allowing them to overlap. And now we're performing the intersection operation on our previous two pictures. So for the intersection, you're just asking which regions are shaded in both diagrams. Think of the intersection as being the AND operation. So you want to capture all the regions that are in A and not in B. So if you want to turn this into sort of more logical phrasing, B complement can be thought of as not B. And so this last set, A intersect B complement, could be phrased as A and not B, if you find it easier to think of it that way. Okay, so let's look at our two previous diagrams. We've got these two regions in the first diagram. We've got these two regions in the second diagram. And now what we're doing is we're taking the regions that are shaded in both diagrams. So that would just be this region here. And so that's our Venn diagram for A intersect B complement. So let's try one more example like that, but this time we're going to have three sets, A, B, C, involved in the situation. So let's talk about how to draw a Venn diagram with three sets. So you're going to draw a big rectangle representing your universal set of all the elements that you care about. We're going to draw our usual situation of having two circles overlapping. And then underneath that, we're going to draw a third circle that overlaps the first two. And we're going to label these. So the top two will be the sets A and B, and the one at the bottom will be C. So that's what a Venn diagram for three sets looks like. Now let's make a plan for which diagrams we're going to need to draw. First, we could figure out what A union B looks like. Then we could figure out what the complement of C looks like. And once we've got that, we can draw a third and final diagram that shows A union B intersected with C complement. So that's our plan of attack here. All right, so for the first set, first Venn diagram, let's shade in A union B. So that's everything that is in A or B or both. So we're actually getting 6 different regions shaded there. Okay, now let's draw a Venn diagram again, and this time we'll try to shade in the complement of C. So we'll set it up in the usual way. We're going to draw our 2 overlapping circles for A and B, and then draw a third overlapping circle representing C. And this time let's shade in not C. So everything that's not in C. Anything that is outside the circle for C. So you get 3 regions at the top, and you also get this big outer region here. Okay, so 4 regions shaded in total there. Now what we're trying to accomplish is a Venn diagram for this thing here. Well, we've got A union B in our first diagram, and we've got C complement in our second diagram. So now let's look at the operation that we're doing. We're doing the AND operation. So you're looking at your 2 previous diagrams, and you're saying which regions are shaded in the first diagram and in the second diagram. And being the key word because it's an intersection. So which regions are shaded in both diagrams? It's the 3 regions near the tops of the circles. So there we go. That's our Venn diagram for A union B intersected with C complement. So last idea we want to look at here is something called De Morgan's laws. De Morgan's laws tell us how to apply the complement operation to a union or an intersection. So there are 2 laws here. Let's take a look at them. So first rule says that if you take the complement of S union T, what you get is S complement intersected with T complement. So the caution here on the side is notice that the operation is reversing. We've got a union on the left side, but we've got an intersection on the right side. So it's like you're passing the complement operation onto your sets, but then the operation is reversing. So there's a second rule to go with this. If we took the complement of an intersection, you can pass the complement onto your individual sets, but again, the operation reverses. So if it was an intersection before, now it's a union. So a good way to understand why De Morgan's laws should be true is just by using a Venn diagram. So let's do an example where we confirm one of these rules. So we're going to confirm the second rule using some Venn diagrams. Now, incidentally, there's no particular reason why your sets have to be called S and T here. So we could equally well rewrite this rule just using our familiar A and B. So that would say the complement of A intersect B is equal to A complement union B complement. The important thing to remember with De Morgan's laws is that the operation is going to reverse. So if you had a union or if you had an intersection on the left side, you're going to have a union on the right side and vice versa. So to confirm something like this using Venn diagrams, what we're aiming to do is draw a Venn diagram for the left side and also draw a separate Venn diagram for the right side and just confirm that those two Venn diagrams are equal. It might take a couple of steps to get those two diagrams done. So let's say our goal is to draw a Venn diagram for the complement of A intersect B. Along the way, we might want to do A intersect B first and then draw the Venn diagram for the complement second. So let's do that, and that will give us the left side of the equation. Okay, so usual setup for Venn diagrams with two sets. You just got each of your sets represented as a circle. And if we're trying to represent the intersection, we're just talking about all the elements that are in both A and B. Okay, now what we would like to do is take the complement of what we just drew. So we would be capturing the region, the three regions that were not shaded in our previous picture. And we can label our sets A and B there. Okay, now what we want to do is confirm that the left side of the equation is equal to the right side of the equation. So what we're working towards is a second diagram that shows A complement union B complement. And then we can do as many warm-up steps or intermediate steps to get there as we want. So what I would suggest is maybe we draw a diagram for A complement, and then we do one for B complement. And then from there, we'll be able to have this A complement union B complement, and that's going to be the right side of the equation. So what we want to show is that the two diagrams that are highlighted here are equal. All right, so let's work towards that. We'll draw our usual setup here, two overlapping circles. A complement is everything outside the circle for A, so two regions shaded. B complement, everything outside the circle for B, so that would be two regions shaded. And for our third diagram here, we're doing the union operation on our previous two diagrams. So let's draw our setup. Okay, when you're taking the union, you're taking everything in the first diagram or everything in the second diagram or both. So anything that is shaded in at least one of the diagrams. So we're definitely getting our outside region. We're getting this left part of the circle. We're getting the right part of the circle. So in total, three regions that are shaded. And now we can come to our conclusion. So yes, the left side of the equation, which is represented by this diagram here, is identical to the right side of the equation, which is represented by that diagram there. So I think I'll just write this in words. The two diagrams are equal, therefore we know that the left side of the equation is equal to the right side of the equation. So that's visual proof, you could say, that De Morgan's laws are true. So here's sort of a real-world example of De Morgan's laws just to show you how this might work in action. So let's say you're going out to dinner with a friend and your friend asks you, okay, what kind of food do you feel like? So something like S union T could represent the fact that you say, I'd be fine with Spanish or Thai food. Now, if you negate that, so we're saying the complement of S union T, well, the negation of an or is actually an and. The negation would be, I don't want Spanish food and I don't want Thai food. And if we re-express that, then we could say, oh, that means the complement of S union T is really the complement of S intersected with the complement of T. So let's talk briefly about why we might care about De Morgan's laws. This comes up when we're trying to simplify a set. So suppose we have something like A union, the complement of B, complemented. We could use De Morgan's laws to simplify that. Well, the laws say that you can pass the complement onto your individual sets. So we'd have something like that, but the operation in the middle is going to reverse. So it's no longer a union, now it's an intersection. And we could take this a little bit further by looking at the second set. If you have a double complement, that just gives you back your original set. That's because logically, if you say not B, that's the same thing as saying B. So a simplified version of your set would just be A complement intersect B, and then that's something that we could draw in a Venn diagram or work with in a follow-up question. So that's the benefit of De Morgan's laws. So we've seen the inclusion-exclusion principle, and we've also started to work with Venn diagrams. Thanks for watching.